Today we're going to do a quick review for the Core 2 test. This is most of the stuff you're going to need to know, and we're going to go over each one. So we'll start off with inertia. All you need to know about inertia is as mass increases, inertia increases. That is due to the force needed to move object will increase, causing inertia to be greater, but remember inertia is not a force. Friction, you need to know force of friction is equal to normal force, Fn, which most of the times will be the force of Earth, mg, but not all the times, times mu, which can be static or kinetic. Kinetic will be one flat number, constant number. Static will be your critical force of friction. That's static, like right before it goes into kinetic. F net, you just need to remember F net is the sum of forces in an object. It's equal to ma. Position, velocity, acceleration. Move this one over here. Remember that position over time could look like that. It's in meters. Velocity, if that's your position, you're going to have a positive slope. So you're going to have positive velocity. That's as a slope. And that's going to be in meters a second. And then your acceleration is going to be a constant acceleration because it's a constant positive slope. It's going to be in meters a second squared. But let's say your velocity is constant like this. You're going to have no acceleration because there's no slope. Just remember that. Centripetal force, just remember the equation for that. Fc equals, mvt squared over r. And, let me try a little better, squared. M is mass, vt squared is velocity, and r is radius. We'll get your centripetal force. But also remember, Fc is equal to mass times AC. So that means AC, centripetal acceleration, is equal to vt squared over r. Moving on to tension, just remember that you're going to use F net for that one, for your whole system, to get your acceleration. Once you get your acceleration in this equation, you can do tension for one object, and then you can do your force. Most of the time it's going to be your force of Earth minus your tension force. You can solve from there. Interactive force pairs, all you need to remember is A on B and B on A. So like, if you got a force like this, B on A, it has to be equal and opposite to A on B. So there's B, A on B. And they have to be equal but opposite. Kinematics, I'll write over to this side over here. These are important to remember. You got three of them, so you're going to have velocity final, sorry for the handwriting, is equal to velocity initial plus acceleration times time. And your second equation is going to be the magnitude of x, or the change in x, is equal to v initial times time plus 1/2 acceleration times time squared. And then your final one is E final, the velocity final squared is equal to velocity initial squared plus 2a change in x. Critical velocity is mostly going to be used for bend curve. That just means that you're not going too fast or too slow. It's going to be the one where remember, it's going to be car on here. And there's going to be no friction force because it's not going too fast or too slow. So there's no velocity pushing it up or down the ramp. Uniform circular motion is it's when an object. Here, I'll draw a diagram for this one. If you got a circle and you got a point here, and it's rotating around this center right here, you're gonna have your centripetal acceleration, AC, pointing always towards the center. AC is always towards the center. Also, FC is towards the center too. Those are the same thing. They're also pointing the same way. One is just without math. And then your tangential velocity. Tangential velocity and acceleration are going to be tangent to this and be going that way if it's rotating this way. So that's the answer for that one down there. Let me draw that one down there. But it also helps you answer this one. Just remember FC and AC always point towards the center. And it's going constantly around that. Your VT, your tangential velocity over here, is equal to 2 pi r, which is the circumference, over time. So that's just how many rotations it does in a rotation it does depending on time. Bend curve up here. If it's going perfect, it's going to be critical velocity. If it's not going too fast or slow. If it's going too fast, that means it's going up the ramp, which means you're going to have a friction force going down. If you have it going too slow, you're going to have friction force going up. Vertical critical motion is pretty much just like wheel problems when a wheel is moving a vertical path. Torque is equal to force times your radial arm. And this is in units of newtons times mass. So that's your unit. That's your equation for that. Torque that is equal to inertia times angular acceleration. For this one, I like to draw the example. Let's do center of mass first. Center of mass is going to be equal to all your masses and distances. So over all your masses added up together, which is represented over there. So it's just going to be, so you multiply all your masses and distance together, and you divide it by your mass, and you do that for the x and the y to find your coordinate. Angular displacement velocity. I'm going to take these three and do a little example over here. So let's say you got your hinge, then you get your radial arm. You got your force. For torque, you can bring your force all the way down, and you can multiply by that distance to the center. So you can do equals FD, or you can do an Fy variable and find that angle there, and you can multiply your F cosine theta times your radial arm. So there's two ways to do that. First way and the second way. Another example I like to do for torque is for angular displacement velocity. I'll do it right over here. So many arrows. So you get a circle here. Let's make that big. Actually, let's do it over here. So you got your circle. You got your radius. And you got your theta. And you got your arc length. And your theta is your angular displacement. Remember that S equals your angular displacement times your length of radial arm. If you divide everything by time, divide these two by time. So if you divide that by time, divide that by time, you get velocity equals angular velocity times radius. Divide those by time. And you get acceleration equals angular acceleration times radius. So just remember that if you divide by time, you get those. Revolutions, radians, just remember one revolution is just equal to whatever your circumference is. So 2 pi r. Because one revolution is one circumference of that. Other thing is if you're changing like RPM into radians a second, just divide it down to revolutions a second, and then you multiply it by 2 pi, because one revolution is equal to 2 pi. Moving on to static equilibrium, just remember F net equals 0 and torque net equals 0. And just solve from there. Tangential velocity and acceleration, it's just tangent. Did it over here, it's just tangent to AC and FC. And that's your equation for tangential velocity. But this is pretty much all you need to know. It's mostly just your equations. I did forget one more thing, is your kinematics for angular displacement and velocity. That's your kinematics, but for these angular displacement and velocity. And I will put them right over here. So it's pretty much just like these kinematics over here, but you just change out with angular displacement and velocity and all that stuff. So you got angular velocity final is equal to angular initial velocity initial plus angular acceleration times time. Then you got your angular displacement is equal to your velocity initial times time plus 1/2 angular acceleration times time squared. And your last one is just going to be your angular velocity squared is equal to your angular initial squared plus 2 angular acceleration over your angular displacement. I believe that's all you need to know. Atwood machines just go into this tension, and I made another video for that if you need. I believe that's all you need to know. Just don't forget to use these equations when you're given problems, and don't be afraid to ask questions.